All right, let's graph some rational functions. So today we're going to be looking at how do you graph a rational function. But first of all, what is a rational function? So just as a rational number is a number that can be expressed as the ratio of two integers, like 2/3, a rational number like 2/3, a rational expression is an expression that can be expressed as the ratio of two polynomials. So one polynomial over another polynomial. So for example, like 3x squared plus 7x minus 4 is a polynomial. And if I divide it by another polynomial like 5x squared minus 2, then I formed a rational expression. A rational function is any function defined by a rational expression, such as r of x equals the ratio. So right now, this is a rational expression. If I say f of x equals that, then I've turned it into a rational function. And so what that does is it lets us graph the rational function. One thing to note is that the q of x, or whatever's in the denominator, is not allowed to equal 0. So that's because we are dividing, so you're not allowed to equal 0. And so this is a rational function. So we're going to look at the graphs. Just a reminder, here is what the graph of a rational function can look like. It's got these dotted lines that are horizontal asymptotes, dotted lines that are vertical asymptotes, and then these curves form the rational function. So we're going to look at how to graph a rational function today. Before we do example 1, though, last class we talked about the transformations. If you look at the parent function, I misspelled that, parent function, y equals 1 over x, then I can graph the parent function and then shift this parent function to the right, left, up, or down based on the transformations I can see. So we talked about k being the vertical shift, h is the horizontal, a would be the vertical stretch. The problem is that not the rational functions are not always written in this form. Most of the time they're written like this, just like the fraction. So I can't see a number being added on the end. I don't just have a constant at the top, I have a variable. So one option that I can do is I can rewrite the rational function to identify the asymptotes and graph. So I can rewrite that using long division. So you have example 1 in your workbook, but go ahead and change example 1 to match this problem because it works out a little bit more nicely. So we're going to do this with long division. So what I'll need to do, this is 4x divided by x minus 3. So 4x is getting divided by x minus 3. And then I'm going to do some long division. So look here, x times 4 would be 4x. I'm going to distribute this 4 to the x and the minus 3. So 4 times x is 4x. 4 times negative 3 is negative 12. Then I'll draw my line and subtract. So that means I'm changing every sign. I get 0 plus 12. So the quotient would be 4 with a remainder of 12. Or I can rewrite it as, 4x divided by x minus 3 is the same as 4 plus my remainder 12 over the x minus 3. Because I divided 4x by x minus 3 and got 4, and 12 was my remainder, so I put it over x minus 3. So that means that g of x is equal to 4 plus 12 over x minus 3. And writing it in this form allows me to see the transformations from the parent function. So this 4 is that k. So that k can sometimes show up at the end or at the beginning, but it needs to be the constant that's by itself. So this 4 is my vertical shift. So the vertical shift would be shifted up 4. Then I have this minus 3 right here. So everything would be shifted to the right. I know it's right because that's a minus, right 3. And then that 12 is the vertical stretch of 12. Now, when you do transformations, they have to be done in the order of operations. So you start by looking at the x, and then what is the first thing that would happen to x? That -3. So the right 3 is the first shift that happens. Then this x would be the 12 would be divided by the x, so that's where the vertical stretch by 12 would come in. Then we would shift it up 4. So those transformations need to happen in that order. So here I have the parent function right now graphed 1 over x. Right here, this is the graph 1 over x. Okay, so let's shift everything. So everything's going to be shifted to the right 3. So everything gets shifted to the right 3. So that means the vertical asymptote would be shifted to the right 3. This part would be shifted right 3. 1, 2, 3. 1, 2, 3. And then this would be shifted to the right 3. 1, 2, 3. Okay. Then the vertical stretch of 12 means all the y values get multiplied by 12. Right now this y value is 1, so it's going to be 12. So it's shift up. This will shift way down to -12. And then up 4. So everything's going to be shifted up 4. Move the line. 1, 2, 3, 4. And then this part gets shifted up 4. 1, 2, 3, 4. So somewhere around here. That's a rough sketch of what it would look like. But what we are asked are to identify the asymptotes again. So everything's going to be shifted to the right, 3, up 4. That really changes my asymptote. So there was an asymptote at y equals 0, but now there's an asymptote at y equals 4. And there was an asymptote before at x equals 0, but now it's been shifted to the right, so it's at x equals +3. Now, if you can use long division to rewrite, that's one option. It's not always going to be easy to do that. So here's another approach to graphing rational functions. So we've got all these steps. So the first thing will be to factor the numerator, denominator, locate any removable discontinuities, which are holes. We'll talk about those in a minute. Locate all the vertical and horizontal asymptotes, and we'll be able to do this algebraically. We'll identify x and y intercepts algebraically, and then we'll figure out what's happening around those asymptotes, around those intercepts, and around the rest of the graph. So let's first talk about removable discontinuities. Removable discontinuities occur when a common factor is divided out. So right now I've got y equals x plus 2 times x minus 3 over x minus 3. I notice that I have a common factor in the numerator and the denominator. So I can divide these out. X minus 3 divided by x minus 3. X minus 3 divided by x minus 3 is 1. And so I have y equals x plus 2. So this larger expression does simplify to x plus 2. The only problem is that if I just simplify and try to graph x plus 2, I have an issue. Because this problem, the original problem, is a division problem. And with division, there is one rule that we cannot break, and that is that we cannot divide by 0. So we can't divide by 0. So that means for this original problem, x could not be something that would cause the denominator to be 0. What would x be to cause the denominator to be 0? X. So if x minus 3 were equal to 0, x being positive 3 would cause the denominator to be equal to 0. So since we can't divide by 0, x is not allowed to be positive 3. Okay? So then what does that mean? What does that look like whenever we graph it? Well, y equals, let's start with this. Y equals x plus 2, that's a line. And I can graph the line with the y-intercept. So y-intercept would be 2. So I could put a point at 2, 1, 2. The slope would be this number right here, 1. So if I plot this just like I have in the past, up 1 over 1, up 1 over 1, down 1, back 1, down 1, back 1, and I were to graph my line, I would have something that looks like this. A line, right? Okay, the only problem is that x is not equal to 3, because if x was equal to 3, then in my original problem, I would be dividing by 0. So what does that mean for this graph? It means that this graph looks like a line, except at x equals 3, there's going to be a hole, also known as a removable discontinuity. So that means there is a hole where x equals 3. So that means to graph this, I would graph the line, but then I'm going to go to where x equals 3, 1, 2, 3, and I would erase this part to have a hole. So there's a hole there. And usually, so this is what it actually looks like. It's like this line, and then there's a gap in the other line. Sometimes it's hard to show that in books. So what you'll see a lot is you'll see an open circle to represent that that's a hole there. So that means this function goes on and on and on and on forever, except there's this one gap at x equals 3. And if you're like, oh, Miss Honeycutt, I don't even need to look at that. I'm just going to graph them both on Desmos. Look, if I graph both these on Desmos, they look like they're the same. The blue one is the graph of y equals x plus 2. The red one is the graph of the rational function. However, we know, you and I know, that this red graph cannot exist at x equals 3. But look what happens when I go to 3. Oh, it looks like there's a line there. Now, if you get close, if you know where to look, you'll see that there's actually a hole at x equals 3. The problem is that's a hole at only 3, not at 3.5. So if you zoom in, even if you zoom in really, really, really far, you're still not going to see the graph. But if you click on it and drag, at that instant when x equals 3, there's an actual hole. Now, we're not going to see a lot of holes in this lesson, but you do need to know that they're there. The next step would be to find all vertical and horizontal asymptotes. But if locate and graph all of those. And also note, if there's already a removable discontinuity, then it can't have a vertical asymptote. So if you find that the x if you find that the x had a hole at that point, then the hole would exist and not the vertical asymptote. So here's how we find some vertical asymptotes. To find a vertical asymptote, vertical asymptotes are guides for the behavior of a graph as it approaches a line. So basically, the denominator of a rational function cannot be 0. So to locate a vertical asymptote, you need to set the denominator not equal to 0 and solve. That's where your vertical asymptote will be. So on example 2, you have to find the vertical and horizontal asymptote. So let's find the vertical asymptote first. And I'll abbreviate a little bit. I know my denominator is not allowed to equal 0. So I'm going to set the denominator not equal to 0. So x squared minus 2x minus 8 is not allowed to equal 0. And then I'm going to solve for x. So I'll solve it like I was solving an actual equation. So I will factor this. X times x is x squared. Then I could have a minus 4, a plus 2. So then x cannot, and then I would say x minus 4 is not allowed to equal 0. So x is not allowed to be negative 4, and x is not allowed to be negative 2. So that means that there is a vertical asymptote at x equals negative 2. Oh, wait, hold on. I need to solve for this. X minus 4 equals 0. X would be positive 4. There's a vertical asymptote at x equals negative 2, and at x equals positive 4. And then let's go ahead and find the vertical asymptote in part B. So in part B, I have this rational function. I do want to factor the numerator and denominator to make sure that I don't have any holes in my function. So let's go ahead and factor the numerator, and then we'll factor the denominator. Plus 4 plus 1, 3. Let's see, in the denominator, I could factor out a 3 and be left with x squared minus 4. So then, oh look, it's a difference of squares. So 3 times x plus 2, x minus 2, under x plus 4 and x plus 1. Now the reason I'm factoring the numerator and the denominator is to see if I have any common factors, because if I do, I would cancel those out and that would be a hole. But I don't have any common factors, so there's no holes. Okay, so now let's find that vertical asymptote. To find the vertical asymptotes, I set the denominator not equal to 0. So 3 times x plus 2 times x minus 2 cannot be equal to 0 because you can't divide by 0. 3 doesn't equal 0, so that's fine. X plus 2 cannot equal 0. X minus 2 cannot equal 0. So x cannot be negative 2, and x cannot be positive 2, which means that there are vertical asymptotes at x equals negative 2 and x equals positive 2. Vertical asymptotes. We also have to find the horizontal asymptotes. So to find horizontal asymptotes, there's a set of rules that you're going to need to keep track of. So you need to make sure that you get these rules down. And it has to do with the degrees of the numerator and the denominator of the polynomial. So when I say degrees, the degree of the polynomial is the highest exponent that polynomial has. So that would be the degree of the numerator. And then 3 would be the degree of the denominator. So then we've got 3 cases, case 1, case 2, case 3. If the degree of the numerator is, case 1, less than the degree of the denominator, is that true here? Is the degree of the numerator less than the degree of the denominator? Yes, that's true. That's this one. Then there's a horizontal asymptote at y equals 0. So this graph would have a horizontal asymptote at y equals 0. If the degree of the numerator is greater, no horizontal asymptote. If the degree of the numerator is equal to the degree of the denominator, set y equal to the ratio of the leading coefficients, and this is the line of the horizontal asymptote. So if I look at g of x here, the numerator has a degree of 2, the denominator has a degree of 2, so the degree of the top and the bottom are the same. So I'm going to say that there is a horizontal asymptote at y equals the ratio of the leading coefficients. So the ratio of the leading coefficients would be 5 over 7. It's the numbers in front of the x with the highest exponent, so 5 over 7. So let's find horizontal asymptotes on parts A and B. So on part A, I look and see, okay, the degree of the top is 2, degree of the bottom is 2, the degrees are the same. So that tells me there's a horizontal asymptote at y equals ratio of the leading coefficients, 2 over 1, which is 2. So vertical, horizontal asymptotes. Next one, let's see, here's the original function. To identify the horizontal asymptotes, it's better to look in the original form. Degree of the top is 2, degree of the bottom is 2. So for the horizontal asymptote, I'm going to say there's one at y equals the ratio of the leading coefficients. So the leading coefficient on the top is 1, leading coefficient on the bottom is 3. so at 1/3. So now let's put all of this together and graph. We're going to graph this function, and then here's a reminder of all the things that we need to do. So first thing, factor numerator and denominator. So in part A, the numerator is already factored. There's nothing else I can do. Same with the denominator. Step 2, locate all horizontal and vertical asymptotes. So let's find the vertical asymptote first. I know that the denominator cannot be equal to 0, so x plus 8 is not allowed to be 0, which means x is not allowed to be -8. So there's a vertical asymptote at x equals -8. So I will plot the vertical asymptote now. Vertical asymptote, x equals -8. Horizontal asymptote, going to look at the degrees. The degree of the numerator is 1. The degree of the denominator is 1. So they have the same degrees, which means there's a horizontal asymptote at y equals the ratio of the leading coefficients. So 4/1, or y equals 4. So I'll plot the horizontal asymptote now. Okay, so check, check. X and y intercepts. So let's find the x-intercept. X-intercept is whenever the y is equal to 0. So if I say 0, because f of x is the same as y, so 0 equals 4x minus 3 over x plus 8. I'm going to multiply both sides by x plus 8. Because what that does, x plus 8 times 0 is still 0. And then on the right side, that cancels out the x plus 8 in the denominator. And I have 4x minus 3. 0 equals 4x minus 3. Add 3 to both sides. 3 equals 4x. So 3/4 equals x. So there's an x-intercept at 3/4, 0. And I'll plot that now. 3/4, 0. Right here. And now for the y-intercept. The y-intercept happens whenever the x is equal to 0. So I take this equation, y equals 4x minus 3 over x plus 8, and I substitute 0 in for the x. So y equals 4 times 0 minus 3 over 0 plus 8. Y equals, I'm getting -3/8. So there's a y-intercept at 0, -3/8. 0, -3/8 is about right here. So I've done this. Now it's time to determine the behavior of the graph around the asymptotes. So now we're going to graph this on Desmos to figure out what's happening. So here's what Desmos shows when I first graph it. There is that x-intercept at -3.75, which is -3/8, and there's the x-intercept at 3/4, 0. And here's what it looks like. And if you're like, well, Ms. Honeycutt, why don't we just graph it on Desmos in the first place? Because we need to, in our heads, have a good idea of what it looks like. And we're also not going to be able to find some asymptotes unless we can find them algebraically sometimes, because sometimes those asymptotes are a little bit tricky. But I also, if I had just graphed this on Desmos, I would just see this picture. I might think that this is what that graph looks like. But having sketched it out and knowing in my head what a reciprocal function does, then I know that this graph should do something like this. Whoa, kind of like be curvy here and then curvy probably up here somewhere, right? So I know that I should see this part, but I should also be able to see this part over here. So me knowing that is an indication to me that I should zoom out until I see the entire graph. So now I can see what the graph looks like. If you try to rely on Desmos too much, then you'll either just look at this and be like, yeah, that's it, or you might just be stuck zooming all the time and not know for sure. So it is important to know what the graph is going to look like. So let's skip ahead to example 5 and graph this one. It's a little more complex, so let's see what that means. All right, so number 1, factor numerator and denominator, see if there's any removable discontinuities. So we're going to factor the numerator, g of x, top factors, let's see, x and x, 6, 1, minus 6 plus 1. And then in the denominator, if I factor out a 2, I'll be left with x squared minus 5. And it looks like that's as far as it factors. I'm not seeing any common factors, so that tells me there's no holes. Again, I would know if I had holes if I had like an x plus 1 up here and an x plus 1 down there, but I don't have any holes or any removable discontinuities. Locate and graph all vertical and horizontal asymptotes. So let's find the vertical asymptote first. So I know my denominator is not allowed to equal 0. 2 doesn't equal 0, that's fine. X squared minus 5 is not allowed to equal 0. X squared is not allowed to equal 5. And since it's it's x squared, I can take the square root of both sides. Remember, I'm solving an equation, so anytime you take the square root of both sides, you need a plus or a minus the square root of 5. Anytime you solve an equation and you take the square root, you need a plus or minus. So that means I actually have 2 vertical asymptotes. I have a vertical asymptote at x equals the positive square root of 5 and x equals the negative square root of 5. And then I'm going to turn those into decimals to kind of figure out what those are. That's approximately positive 2.236 and approximately negative 2.236. So I'm going to sketch those now. Okay, positive 2.236, negative 2.236. Okay, now let's find horizontal asymptotes. The degree of the numerator is 2. The degree of the denominator is also 2. Since they're the same, there's a horizontal asymptote at y equals the ratio of the leading coefficient. So leading coefficient here is 1, 2, so y equals 1/2. I'll plot that horizontal asymptote. Okay, check. Identify an x and y intercepts. So for the x-intercept, that's when y equals 0. So 0 equals x squared minus 5x plus 6 over 2x squared minus 10. So again, I'm going to multiply both sides by the denominator to cancel it out. So that cancels it out on the right. On the left, 2x squared minus 10 times 0 is 0. So I just have 0 equals x squared minus 5x plus 6. I've already factored that once. It factors into x minus 6 times x plus 1. So I get that x equals minus 6 plus 1. Well, I factored it once, but I factored it incorrectly. Let's fix this. Let's try this again. Factoring x times x would be x and x. I need to multiply to get positive 6. So 2 times 3 is positive 6. Make them both negative. They'll add to be negative 3. So that just means I need to change this part up here, the numerator. X minus 2, x minus 3. There we go. Okay. That doesn't affect anything else in the problem. Yay. Okay. So 0 equals x minus 2 times x minus 3. Set both of those equal to 0. X minus 2 equals 0. X minus 3 equals 0. So I get that x equals 2 and x equals 3 are my x-intercepts. So I'll put a point at positive 2 and positive 3. Then for the y-intercept, I'm going to substitute 0 into the original equation. So y equals 0 squared minus 5 times 0, which is 0, plus 6 over 2 times 0 squared is 0, minus 10. 6 divided by negative 10 is negative 3/5. So there's a y-intercept at 0, negative 3/5, which is about like right there. And I'll graph all this on Desmos. And here's what I have on Desmos. Let's make sure everything looks right. There's my x-intercepts. There's that y-intercept. And then, yeah, it looks like I've got my asymptotes plotted correctly.